In calculating probabilities for intersection, union, and complement, I've got a couple of examples here. We're going to assume that both spinners must be spun, and we're going to calculate the following probabilities. So I went ahead and created the model for us to be able to hopefully extract some of the probabilities from this. So let's take a look at the questions down at the bottom. So with the probability of D and 4, so we want both of those things to happen simultaneously. So what we're going to do is we're going to take a look at the probability of D occurring and then the probability of 4 occurring. And what we're looking for specifically is the overlap or the intersection between those events. So in this case, we're going to end up with 4 over 64. So that location where D and 4 overlap right there. So our probability of D and 4 over 64, which can be simplified, but it's not really necessary. Okay, the next one here, we want the probability of D or 4. So either of those would be a success for us. So the probability of D, everything in that column represents a probability of spinning D. So that column, we can go through and add up the 16 over 64, and we can add up the 8 over 64, and we can add up the 4 over 64, and we can add up the other 4 over 64. If we add those together, though, we do have to get the total of that column, which was 4 eighths. So I propose that we go through and take the 4 eighths with us. So if I take the total there for D, I'm going to take my 4 eighths. So that's just for D. Or, okay, so plus, we're also talking about the probability of 4 being a success. So we have the same scenario here. We could add up all of the elements within that row that account for the probability of 4, or we could just take a look at the total for 4, which is going to be 1/8. So I'm going to take that 1/8. Now, the issue here, and I don't want to stop now, is that if I go back and take a look at the probability of D highlighted and the probability of 4 highlighted, you'll notice that we have one of the squares or boxes inside our model was actually double counted. It was included in the column of D, and it was included in the row of 4. So that 4 over 64 was included in both the yellow highlight and in the green highlight. We want to include it in the answer. We just don't want to count it twice. So what we're going to end up doing is we're going to be subtracting that 4 over 64, so that overlap that was counted for the 4 and for the D. So we're going to go ahead and subtract that 4 over 64. So that's going to be our double count. We're going to go ahead and figure out what this probability is. And the calculation for this comes out to be 9 over 16. That is the simplified version. You don't have to give the simplified. You could have gone through and matched the denominators and then subtracted. Okay, moving down to the next one. So the probability of not D. So anything besides D would be a success. So if we go back up to our table, so not D. So A would be good. So anything in that column for A would be a success because it's not D. Anything in column C would be good because it's not D. Anything in column E, and likewise anything in column F. The other thing that we could look at is, well, what about the rows? Take a look at row for 1. Notice that the 4 over 64, the 4 over 64, the 4 over 64, and the 4 over 64 were already counted in the yellow, so we don't want to double count it. The only one that we would be counting new is the 16 over 64. However, that's in the D column. That's not what we want. So I think what we could do here, and we'll see the same issues with the 2, 3, and 4, is if we go through, we could just count the ones for A, C, E, and F. So one way to do it is we go through and add up the 1/8 for A, 1/8 for C, 1/8 for E, and 1/8 for F. So that's one way to do it. Another way to do it, though, so one way to do it is to add up all 4 of the other ones. So 1/8 for A, 1/8 for C, 1/8 for E, and 1/8 for F. which we know is going to give us 4/8. So that's one way to do it. There's another way to do it, though. If you want the probability of not D, well, since everything else is D, you can figure out what D would have been. And since probability has to represent 100% or 1, we could do 1 minus the probability of D itself. This is called the complement. So, and here at the bottom, what I could have done is 1, so this is equal to 1 minus the probability of getting D. So this would be 1 minus 4/8. But if you subtract those, you still get 4/8. So regardless of how you handle it, you're still going to get the exact same answer. Okay, so certain populations, 60% are male, 40% are female. It's known that 8% and 3% of male and female respectively are colorblind. So I went ahead and put our model down here. What we're going to do is go ahead and answer some of the questions. Probability of randomly select person population in the population is male and colorblind. So the way that the tree diagram works out, it's much like an area model, but so we're still going to do multiplication down our branches, what we did previously, or how we set up the model itself. We're trying to find that single branch that is, or possible multiple branches, where we have male and colorblind. So if I do male and colorblind, that's going to give me that branch. So in this case, I'm going to get 0.048 as my probability. Okay. 2, we take a look at 2. I have some color coding on this one. It's a probability a randomly selected person in the population is female or not colorblind. Okay, so female, we've got multiple branches for female. So what we could do for female is go all the way down that branch, since female is in that branch. This one also is in that branch. Say, or not colorblind. Okay, so we have not colorblind. I'll grab another color here. So not colorblind, I'm going to go to the end here. That's not colorblind. This is also not colorblind. So this is a lot like when we did the area model where we had stuff that kind of overlapped. So what I would do is go through, figure out the probabilities at each of those branches. So all the orange branches, then we have all the purple branches. But notice that one of the branches is both purple and orange. So we just want to make sure that we don't double count that. So if we kind of set up a tiny bit of an equation here to help us out. So we would do the probability of female plus the probability of not colorblind but then since there is an intersection between female and not colorblind, we just don't want to double count that. So probability of female and not colorblind. We're just not double counting, that's all. So in this case, probability of female, well, probability of female is the purple branches. So if we have all the purple branches, we would have 0.012 and 0.388. So female itself, 0.012 plus 0.388 plus probability of not colorblind. Well, probability of not colorblind are my orange branches. So that's 0.552 plus 0.388 minus, and we can actually see that overlap happening where we kind of doubled up the calculation. Notice that 0.388 was included in both of those. It's not that we don't want to include it, we just don't want to include it twice. So we would end up having to subtract the branch that is both orange and purple, which is the 0.388 branch. Or we could just say, okay, well, it's the 0.552, the 0.012, and the 0.388. We don't have to worry about the double counting part. So all this 0.388, is just to eliminate that double count. That's all it is. Let me go ahead and calculate this. And we do end up with 0.952. Okay, last question. It's probability a randomly selected person in the population is not male. Okay, so probability of not male. I'm going to go ahead and use that complement. So that would be 1 minus the probability of male. Well, if I take a look back, and I can actually look back at the original part of this question. So I'll go ahead and highlight this in red. We know that 60% are male. So we would do 1 minus probability of male would be 0.60 or 60%. And if I go ahead and subtract that, that would give me 0.40.